Good morning, Astronomy 1020. Welcome to our third lecture, where we will learn the details of Kepler's laws and planetary orbits. And if things go well, transition into some of Newtonian physics, learn Newton's laws of motion, learn about forces and accelerations and other such things that will build up to an understanding of how planets and stars orbit one another through gravity. Today's lab is on making a Keplerian ellipse, a fun, simple, and very instructive lab. I'm going to go ahead and see if I can find our lab tab and hit print right now. But I'd like to mention that if you really want to do today's lab proper, there's a couple of simple things that we might need to do this, to do it right. There's a couple of different parts of this lab, but I'm at least going to have us focus on this one here. This is the page that I want, 5-5. So I'm just going to hit print, and I'm just going to hit custom pages, just page number 5. That should be the only one that you need. There's a really cool part on measuring the eccentricity of the moon's orbit, but I don't know if we're going to have time for it, in all honesty. If you do want to do this lab correct, the materials that you would need to scrounge up around your house are just a piece of cardboard. You can cut something off of a wine box with a box cutter, a simple ruler, a length of string, which I've tied into a knot here to help us make our orbital ellipse. And the length of string, once it's tied, is about 15 centimeters long, approximately, maybe 16 centimeters long. That would be about, so probably double that, right? You'd probably want to make it 33 or 34 centimeters, and then tie it into a little knot. And that loop of string is what you would need. You don't want it to be flexible like a rubber band. And then a couple of push pins or thumbtacks that you might find in your arts and crafts drawer. And then, of course, this page. This page would be easy to reproduce if you don't have a printer. You would just need to draw 2 dots. Please note the separation distance, which is, I think, 12 centimeters between the 2 focus points. And you'd have to reproduce these at the bottom of the page. So if you don't have a printer, you're going to make me this, the 2 focus points 12 centimeters apart, and those lines there as well. For those of you who truly cannot even handle that task, and I know you're out there, if you're really hard up for some reason, from anything from physical disability to just very difficulty just doing, little arts and craftsy tasks like that, I did make my own ellipse that you could work from. This is not the best thing to do, because part of the little exercise today is to build your own ellipse. But if you really just can't handle it, then you could use mine and proceed from there. I don't know if I should be doing this, but I'm doing it just so that everyone can get the job done. Things are difficult as it is right now. Okay, so keep that in mind. We'll be doing that lab later on. Let us get into Kepler's laws and Keplerian ellipses. As I told you last time in our micro history lesson, Johannes Kepler was an interesting German astronomer and mathematician. But also a mathematician who worked for a famous astronomer, a famous Danish astronomer named Tycho Brahe. And the time period for this, I believe, was the 1600s. I might actually want to get my history lesson that I'll be covering in my 1010 class. Those of you who are taking my solar system class get a little bit more robust of a history lesson, but we unfortunately don't have time for that if we want to get to everybody's favorite topics like black holes and such. And Johannes Kepler, here are the dates of his birth and death, works for a famous astronomer named Tycho Brahe, who is attempting to carefully observe the positions of stars and planets to determine whether the Copernican sun-centered solar system or the old Ptolemaic geocentric solar system was the proper understanding or the proper model of the motions of the heavens. And for these people, big things depended upon it, because as you know, subjects of astronomy and the universe get tied into cosmology and philosophy and even theology. So these people felt like they were arguing about the nature of everything from reality to God when they tried to determine whether the Earth was the center of the cosmos or the sun was. Although Johannes Kepler worked for him at the famous observatory, and here's an old woodcut of the great Tycho Brahe and his assistant Johannes Kepler taking measurements of planets and stars. And they were at a legendary observatory on an island off Denmark called Uraniborg, which the Danish king had given to them for these observational purposes. So Tycho Brahe and Kepler and some friends collected positions of stars and positions of planets over many years with very careful positional resolution, the best that could be done with the naked eye. And this was just before telescopes were invented. And unlike his boss, who was open-minded as to the question about whether Earth was the center of the cosmos or the sun was, Johannes Kepler was sort of already biased towards the Copernican solar system. He believed it was more elegant. So he was a devout Copernican, meaning he believed in a sun-centered solar system. The same theory which is dominant in our physics today. And his idea was he wanted to sort of build a working model of the Copernican solar system, one that would be able to sort of reflect slash predict the orbits of planets, moons, and stars. Copernicus had built a model of the solar system that supposedly would predict the positions of planets and stars in the sun. But Copernicus suffered from a problem, a philosophical bias that went all the way back to Plato in ancient Greece. He believed, like the ancient philosophers did, that the heavens were somehow a magical place that was timeless, eternal, and unchanging, and that the only geometry which could properly express the orbits of planets in the heavens were perfect circles, because circles were like this heavenly geometrical form and they have no beginning and no end. And in particular, people were worried that if the heavens were not perfectly circular, then over time the heavens would become unwound and the orbits would not close on themselves, which actually the heavens do become unwound over time. It's just over a time scale that no one could possibly fathom at the time. Kepler, being the mathematician that he was, discovered that he could fix the Copernican solar system and actually make it predict the proper positions of the planets if he gave up on the obsession with perfect circles and instead modeled the orbits of planets on one of his pet subjects, ellipses. And ellipses, which for the moment we'll call squishy circles, are part of a class of geometrical shapes called conic sections. And it turns out that there are a number of limited ways in which you can slice a cone and create a two-dimensional shape. If you slice a cone horizontally, the two-dimensional geometrical shape that results is a circle. If you slice a cone at an angle, you get a shape called an ellipse. If you slice it through the bottom, you get this U shape called a parabola. And if you slice it vertically, you get another U shape with a slightly different geometry, and that's called a hyperbola. Circles, ellipses, parabolas, and hyperbolas are all known as conic sections. And they're an important class of geometrical objects that, that all describe the orbits of gravity. It turns out that, although I'm not entirely sure how keyed in on this Kepler was, but these four shapes are the four shapes that result when two bodies interact with each other gravitationally. And Kepler had sort of stumbled upon the first level of truth, which was that in general, orbits that are bound are more ellipses than they are circles. And that was a huge deal. We'll take that as a note in just a minute. Let's talk about how one goes about making an ellipse. And this is what we're going to do in our lab today, simple though it may be. An ellipse actually has a very technical mathematical definition, but it involves some trigonometric functions which might give people the willies. A nicer way to do things is to take a couple of thumbtacks and put them into some cardboard at 2 points called the focus point. And the focus points are going to be equidistant from where the center of the ellipse will be. And then we're going to tie a loop of string around those two thumbtacks. We're going to put our pencil into the string so that it makes a little triangle. And we're going to keep that string tight, keep that triangle at the same perimeter. And then as we drag the pencil around the paper, an oval shape will result, which is technically an ellipse. The mathematical definition of the ellipse is that this triangle here must maintain the same perimeter, no matter what point of the ellipse that you are on. So it's easy and fun to make an ellipse. And why don't we start by making a cheater version on our notes here. So let's finish up. So, so Kepler, his famous thing was that he modeled orbits as ellipses, and we'll put in parentheses, not circles. And he did this using orbital data for the positions of Mars. In other words, Tycho Brahe, and probably himself, carefully recorded the positions of Mars down to a positional resolution of about 3 minutes of arc, which is the best that you can do with the human eye. And then using those positions of Mars, he sort of modeled the shape as an ellipse and discovered that he could predict where Mars would be next, which gave him sort of great assurance that he was on to something, okay? So he sort of built this model, and this model worked, and it had predictive power. That's the thing that we say in science. If your model has predictive power, then it gives people confidence that you know what you're talking about. And from here, he went on to develop a set of laws for planetary orbits. So he wrote, in particular, he wrote several books, but one of his important ones, the watershed one, was Harmonices Mundi, on the harmony of the spheres. I think this is how you spell it in Latin. And in it, the important thing that he did, which has really survived the test of time, are his 3 laws of planetary motion, which give us good judgment about how a planet moves around the sun. So these are 3 laws of planetary motion. That's what we want to start with today. Hopefully you guys can read this at the bottom, sorry. Okay, before we do 3 laws of planetary motion, it would be a good idea for us to make a quick and dirty model of an ellipse like the one that we'll do in our lab more carefully today. I would like to erase this. I don't know if you guys have caught up to me. Anyone need a second here? Or are we good? All right, here we go then. So let's make a quick model of an ellipse. The way I'm going to do this is I'm going to take a ruler and model of an ellipse. We're going to leave some headroom here, and we're just going to cheat, and we're going to make a line. I guess I'll make mine 50 centimeters long, and I'll mark the midpoint. You guys might want to do 12 centimeters, or actually maybe even 10 centimeters. I think would be good for you guys. Make a 10 centimeter line and mark it at 5 centimeters. I sort of did a crap job measuring here. Okay. Then once you've marked the midpoint, sort of make a line that is shorter. Like so, as a vertical cross, and then connect the edges in a sort of quick and dirty oval. This is not really how we do an ellipse, but it's close enough. It should kind of look like a football shape. Obviously, the one we do in lab today will look a lot better than this. But we just need some definitions before we go forward. Now, the focus points should be mathematically prescribed, but we're going to just sort of cheat, although I will try to make them equidistant if I can. Okay. Okay. So the focus points are called F1 and F2. And focus points are part of the geometry of an ellipse. The center of the ellipse is here. The line that cuts through the ellipse is called the, well, let's see, how do we do this? This diagram is going to get a little busy because I made my ellipse kind of small. So the major axis cuts through the ellipse like a football, like the long dimension of a football. The minor axis runs up and down. And then there are two parameters of extreme importance, which I'm realizing I did not leave enough room for. The first is this distance. Oh gosh, I'm really annoyed with myself right now because I did not make my ellipse big enough. So just a second, guys. I'm going to try to do this a little faster, a little better. I realize I just need a little bit more room. Hopefully you didn't run into the same problem I did. F1, F2, major axis, minor axis, focus points, and then the two parameters that are extremely important are this distance here. The distance from the center to a focus point is called x. And x is sometimes called the focus length, or I like to call x the focus offset. It's how far the center is from the focus of the ellipse. And if you want, sometimes we just mark the center with a little c. Hey, I can hear like dishes and dishwashers and things in the background. Who's making noise back there? Ashley, Don't forget to mute yourself. Okay. The second parameter that is extremely important in today's lesson is the distance from the center to the edge of the ellipse. And this distance here, A, gets its own letter. A is known as the Semimajor Axis of the ellipse. Very important parameter in astronomy. It's half of the major axis, a very simple concept. Ellipses can have a varying degree of squishiness. They can go from perfectly circular all the way to practically cigar-shaped. And the parameter which measures this is called the eccentricity. And this is one of the reasons we had to do this before we gave you Kepler's laws. Let's let the letter E stand for eccentricity. Eccentricity is the percent squishiness of the ellipse. E has a domain which goes from 0 all the way up to, but not including, the number 1. So the eccentricity, for example, can be 0, 0.1, 0.5, 0.999 forever, but it's not allowed to be a number 1. And as you change the eccentricity, we go from circular all the way to cigar-shaped. So an E of 0 for now, we can call a circle. And an E of 0.999 sort of looks like that, all right? Here's a good rule of thumb. An eccentricity of 0.5 kind of looks like an egg. I'll show you a picture of some varying eccentricities in just a moment. The eccentricity can be measured through stratagems, or if you know your focus offset and your semimajor axis, you can calculate your eccentricity, as we will do in our labs today, by doing x divided by a. So it turns out the eccentricity is the ratio of what percentage x is to the semimajor axis. Notice that if the focus offset goes to 0, if your two focus points move to the center of the ellipse, then x is 0 and a is the radius of a circle. So for a circle, a would be the radius. Before we write down Kepler's laws of planetary motion, let's let you all get that into your notebooks there. Handwriting wasn't awesome today. And let's go ahead and let's call up a cute little Google graphic. This one here. I like this cartoonified. Yeah. I want you guys to look at function, wait, control plus, some varying eccentricities. You'll notice that an eccentricity of 0, the red image, is a perfect circle. Notice that with an eccentricity of 0.2, which might be considered 20% squishy, the orange shape actually looks pretty circular to the naked eye. By the time you get to 0.5, egg-shaped. By the time you get to 0.9, strong oval. And then as you get above 90%, it really starts to look cigar-shaped. Okay. If you look at the orbital data, if you look at orbital data for the planets, let's call up the orbital eccentricities of the planets. eccentricities of planets. And I'd like us to see like a quick table. Planetary fact sheet. They have a few here. Actually, we can just go with, okay. So here you can see the major planets and Pluto, and you can see their orbital eccentricities listed below. In fact, maybe as part of our learning, we could write this down on our notebooks, but let's round everything to like one significant figure. So if you guys have a lock on this for a second, sort of, take a quick snapshot or take a peek at that. What would you say the orbital eccentricity of Earth is if you rounded to one significant figure?
0.02.
Correct. So in other words, 2% squishy, right? So let's write them over here. So here's the orbital eccentricity of Earth. 2% squishy. I would like to propose to you that a 2% eccentric ellipse is so close to a perfect circle that if I used a computer program to draw a perfect circle and then a 2% eccentric ellipse, and I shuffled them up like 3-card Monte and said, which is the perfect circle, A or B, I think you would have a difficult time choosing the correct one. Your eye cannot really distinguish that unless you're being very careful. On the other hand, let's look at some of the others. Venus is 0.007. That's almost perfectly circular. Mars is actually a little bit more eccentric than the average planet in our solar system. At 9% eccentricity, you're still quite circular, but there's a little bit more squish there. The members of our solar system which are extreme are Mercury at 21%, okay, and Pluto at 25%. And if you look at some of the other minor planets, like for instance, Eris, I believe Eris has an orbital eccentricity of 40%, which is pretty wild. Eris, dwarf planet. Usually when you go to a Wikipedia page for a planet or a moon, one of the important parameters besides the Semimajor Axis is that they'll label the eccentricity. So at 44% eccentricity, the orbit of Eris is pretty wild. And I bet they even have a little diagram comparing the orbits of Eris to that of Pluto. Yeah, check this out. You can see here that Pluto's orbit actually looks circular by comparison. The ellipse that represents Eris's orbit actually brings it interior to the orbit of Pluto and just about scrapes the edge of Neptune. On the other hand, at its farthest distance, at aphelion, 100 astronomical units is pretty much at the edge of our solar system, right? So the eccentricity of a planet is a very important parameter.
This might be a silly question, but could Eris ever collide with, was it Neptune?
Right. And you might ask the same question about Pluto too, because Pluto's orbit comes interior to Neptune. Now, this question is one that I address more in Astronomy 1010, but it's not a silly question, and I will give you the quick and dirty answer. Planets and moons that have been zipping around the sun for 5 billion years exert microscopic little gravitational tugs on each other, and oftentimes they come into a property called orbital resonance. Orbital resonance is where these gravitational objects, and they're not little, I don't know why I'm saying little, they've nudged each other so many times that they've come into perfect lockstep, and they've synchronized their clockwork, they've synchronized their dance. So for instance, here's an interesting and funny concept. Suppose we just took what looked like two random numbers, orbital periods of the planets. I shouldn't go too off-roading on this, but I want to because it's cool. Suppose we looked at the periods of Neptune and Pluto. Oh, what is this nonsense? I just want the damn numbers. Here we go. Which seem to be random numbers. It takes Pluto 248.59 years to go around the sun. It takes Neptune 164.79 years to go around the sun. Those numbers at first look random. I want you to take your calculators and divide the two. So take out your Casio calculator, type in 164.79 and divide it by 248.59 and check out the number you get. Is 0.66 a random number? Is it like the most random number you've ever heard about between 0 and 1?
No.
0.66 reminds me of something, doesn't it? What is 0.66? Anyone know their fractions?
2/3.
That's right. And what that means, if the ratio is 2/3, it means that Neptune completes exactly 3 orbits for every exactly 2 orbits of Pluto. And what that's suggesting is they've synchronized their swim to a point where they will not collide because they've kind of gravitationally synchronized their periods into a kind of delicate lockstep. In other words, if they were going to collide, probably it would have happened already in the 5 billion year history of our solar system. Earlier in our solar system's history, there were many insane collisions happening all the time. But over 5 billion years, things kind of approached a steady state solution where either you got flung out of the solar system, you got flung into the sun, or if you survived, over time, tiny little nudges synchronized your orbits to the other objects. Now, you might think that's kind of a cool coinkydink that happens with Pluto and Neptune, but if you start playing that game and dividing periods of moons all over our solar system, you find these resonances and these harmonics everywhere. Now, I can't remember if Eris has one, but I wouldn't be surprised if Eris also had some kind of a resonance with either Neptune or Pluto. Unfortunately, so 164.79 divided by 557 is 0.29. I'd have to think about that. Let me get back on that later. Anyways, no, they probably won't collide anytime in the near future. Okay, let's do Kepler's laws of planetary motion before I go totally off the deep end here. Kepler's laws of planetary motion are important in our class because they give us good judgment about how gravitational orbits work. And although we're going to start off by considering planets going around the sun, this concept can later be extended to stars and moons and other situations. This is kind of the first time that someone got something really right about gravitational orbits. So it's kind of a natural place for us to start in a week-long lecture on gravity. So introducing, I probably took a little too long doing it, Kepler's 3 laws of planetary motion. I expect you to have these memorized for a test, okay? The first law is called the law of ellipses. The law of ellipses states a planet orbits the sun on an ellipse. That's the first part that matters. And the second part is with the sun located at a focus point. That's the second part that matters. In other words, not only are circles out and ellipses in, but it's not exactly that the proper model for the Copernican solar system is to have the sun at the center of the solar system, but actually the sun is at one of these focus points with the planet orbiting along the black ellipse line here. Of course, that implies that there will be a closest approach to the sun, perihelion, and a farthest approach from the sun, aphelion. And you can actually calculate your perihelion and your aphelion based on the parameters of the ellipse, both the semimajor axis and the eccentricity. You'll remember that we did this in our homeworks last time. These two formulas I kind of associate with Kepler's laws, but these formulas themselves are not a part of it. So at the risk of muddling the message here, we'll tuck those in the bottom somewhere, okay? Okay, the second law is called the law of equal areas, or the law of areas. And to understand what's going on here, I'd like to show you this slide, where Kepler was trying to understand something about how a planet orbits the sun with time. And this was an important discovery because not only did Plato believe that the heavens had to be perfectly circular in their geometry, but he also subscribed to uniform circular motion, which means constant angular velocity. They believed that the rate which planets would drift across the sky should be completely consistent and never change. In fact, if you exaggerate the ellipse, you can see that that is not true. Let's consider the orbit of a planet like Mars. In a roughly 2-month period, the planet might go from point A to point B. And if you look at this length of the ellipse, that's a pretty good fraction of the overall oval. Maybe not quite a quarter of the distance around the ellipse, but getting close to it, maybe an eighth or something. Later on, near aphelion, point G, if you track a 2-month period in the orbit of Mars, it might go from H to I, and you can see that the distance from A to B is much longer than the distance from H to I. So it's not traveling the same distance in the same amount of time. However, Kepler discovered that he could predict the position if he drew a line connecting the planet and the sun, and then he added up the area contained within this triangle here, counted all the boxes, and then he made a similar triangle by connecting the sun to the planets there and there, that the planet didn't sweep out equal distances in equal times, but the planet does sweep through equal areas in equal times. And as if by magic, the area of all the boxes in this little triangle would be perfectly equal to the area of those boxes. And that provides a method of predicting where the planet will be. So the law of areas goes like this. A planet sweeps out equal units of area in equal intervals of time. This law is especially important for understanding gravitational orbits later on. The law that you will use the most is the one that we used in our homeworks last week. That's known as the harmonic law. Oops. The harmonic law is a mathematical expression relating the period to the semimajor axis of the ellipse. P squared is equal to A cubed, where the most important thing to remember are the units. P must be measured in units of years, and A must be measured in units of astronomical units. In fact, Kepler basically invented the astronomical unit because he discovered this law was true and that he could basically measure the distances to the planets in terms of an Earth-Sun distance as a ratio. Unfortunately, Although Kepler could tell you that Jupiter was 5 AU from the sun, 5 times further than Earth, he actually did not know how many miles or kilometers were in an astronomical unit. So the really hard thing wasn't measuring the distances to the planets relative to Earth. It was trying to figure out the Earth to sun distance. And that took at least 100 years until Jeremiah Horrocks basically used a very cool trick of geometry to measure the positions, the angular positions of the planet Mercury during a transit. So once again, I'm going to go off-roading here, and I probably shouldn't. But
real quick, you said P must be measured in units of years and A must be measured in units of AU all the time.
All the time.
Okay, just making sure. Thank you.
Okay, so that's wicked important, Caitlin. And this is going to matter to you guys on your test, because here's a secret to everybody. This is going to be on the test. You're going to need to use this in the test, and you're going to need to remember years in AU for that formula. So in fact, to emphasize how much this matters to you, put a box around it and put some big stars next to it. This ain't no small thing. Okay, obviously P is the period of the planet, the orbital period. The orbital sidereal period, if you're taking my 1010 class, Lionel. A, however, requires a little bit of explanation, because A is what?
AU.
Those are its units, but that doesn't describe what it is.
Distance from Earth to Sun.
Kind of not though. Yes and no. Take a look at our model of an ellipse. This is a nice one, like the one that we're going to build today, right? A is the semi-major axis of the ellipse, right? And that means it's the distance from the center to sort of the edge of the ellipse. It's half of the major axis, where this is the major axis, right? But where is the sun in this ellipse? Or
On the
Model.
sorry, one more time.
the focus.
It's at one of the focus points. Let's, for cleanness of diagram, let's put it, oops, sorry, let me undo that. It's at one of the focus points. You choose, right? So I'll choose this one for now. Where is the planet?
On the black line.
On the black line. Thank you. So, sorry. What the shit is going on here? Okay. Here's the planet. Now, does the distance between the sun and the planet seem to be related to the semi-major axis of the ellipse?
Yeah, that converts into the that small angle, correct?
Not exactly. That I can see why you might have said that, Caitlin.
Yeah.
But I just happened to draw this line. I just drew.
Okay.
My point is there's a bunch of different lines. The planet could also be, I don't know, over here, right? Shoot. Like I just picked one possible position for the planet to be, right?
So it can be indefinitely anywhere within that circle, on the line circle.
But a moment ago, someone said A is like the distance from Earth to the sun.
Okay.
And I'm trying to break that down for a second and say, well, A is a geometrical property of the ellipse, half of the major axis, but it actually doesn't point between the sun and the planet necessarily, right?
Yeah.
However, one could imagine trying to calculate the average distance between the planet and the sun. And this is something that we do in mathematics. We try to calculate the average distance. For instance, we would do so by taking this distance and then measuring that distance. And we would add up all of these 12 measurements and then we would divide by 12, and the average of these lines would be the average distance between Earth and the sun, right? And if we wanted to do a really, really careful job, we would not only average over these 12 observations, but we'd also want to include this distance and that distance. To really do this right, we would have to almost take an infinite number of measurements, correct? There's actually a method to average the distance an infinity number of times, and wait for it, calculus. You can use calculus as a sort of dark magic to average the distance between the planet and sun in over an infinity number of times. And when you do this, the magic of calculus reveals to us that weirdly, although you wouldn't predict it beforehand, the average of all of these lengths turns out to be your semi-major axis. And you can almost kind of see that if you compare the very shortest distance, the perihelion, with the very longest distance, the aphelion, right? Imagine taking the average of these two. You'd add up this length and this length, which would be the major axis distance, and then you would divide by 2, and that would give you the semi-major axis. And it actually kind of balances out for all the other measurements. Okay, that's cool, brah, but what I need you guys to remember is something kind of complicated. A has two meanings, two simultaneous meanings in this class. A is both the semi-major axis of the ellipse, the semi-major axis of the ellipse, but A is also the average distance between the sun and the planet. And that's something that you might have to slow down and think about carefully before you potentially get yourself screwed up somewhere. You know, thank you for coming to my TED Talk about that, as the kids say. What do you think the semi-major axis of Earth's ellipse is? What would be the semi-major axis of Earth's ellipse?
Would it just be 1 AU?
Right. In fact, that's kind of how we defined 1 AU, right? 1 AU is supposed to be the average distance between the sun and Earth. In fact, now we have some more interesting vocabulary to use, right? I could also say 1 AU is defined as the semi-major axis of the ellipse of Earth's orbit. That would be a little egg-headed of me, you know, but then again, ellipses are egg-shaped. So anyways, probably if you needed to cheat, I just tell students A is the distance between the planet and the sun. Weirdly, it is kind of the truth, right? For instance, if you have a circle, and in a circle, a perfect circle is a type of ellipse. It's a special case of an ellipse. For a circle, the orbital radius is the semi-major axis. So that's kind of a special case. Oh, also, because I told you I would, don't forget to throw these formulas in so you have them in your notes. And you can just kind of throw them in anywhere. Not part of Kepler's laws, but you can calculate perihelion as A times 1 minus E, where E is the eccentricity. And you can calculate the aphelion as A times 1 plus E. I'd like you guys to notice my choice of variable. Here I'm using peri as the variable for perihelion. God, I'd hate to confuse that with P on a test. That would be messy. And I'm also using APH as my variable. I'd hate to confuse aphelion with A. That would be a big mistake, okay? I've seen that one before. So hopefully you guys are cool like that. Nice. You guys learned how to do this in homework. Do you think you still have what it takes? Let's find out. May I erase everyone? Any objectors? Here I go. Just a couple of quick examples, just to make sure that we have this. If Pluto, let's see here. Pluto has a semi-major axis of 39 point, I think it's 39.5 AU. So find the period. P squared is equal to A cubed. We could plug this in for A, but I like to solve for the period first by taking the square root of both sides. I always like to start solving algebraically for the variable I want and plugging in the numbers afterwards. That's like math style. That's good math style. So P squared is equal to A cubed. That's how I would write it. And then I would substitute in for my A square root of 39.5 cubed. Now, can you guys handle that calculator operation? Tell me what you get. Why don't you, those 5 or 6 of you who are partying with me today, why don't you punch it and hold it up and just make me feel good about the fact that you remember how to do this. That's what I'm concerned about right now. Let's burn a minute of class time on that. By the way, for those of you watching the video, I am going to show how to punch it as well. I just want to see what you guys can do without me. So hold it up when you get an answer. Thanks, Dennis. Oh, look at, yes, Dennis, correct. Although you haven't, bastard calculator, but okay. What's up with that?
So I texted my dad. He's going to job lot and he's picking me up one. So
Thank you kindly. I love me some job lot like every Rhode Islander. I haven't always noticed the Casio FX260 solar. Did you impress upon him that it has to be that model?
yes, I told him if it's not there, you have to go to literally any other store that has it.
Staples or something like that. Okay.
So,
Thanks for being a good sport.
Fun fact, I work at Job Lot and they do not have those. They have like very run-of-the-mill calculators. They do not have this specific calculator because I checked where I worked.
That's
Well,
wait,
okay,
Caitlin, which
I
one do
still
you
want him to waste his time because he was mean to me the other day. So
Which one's your best bet?
I love Job Lot personally on a side note, but I did, of course, me being me, what do you think the first thing I do when I go to Job Lot? I check out their calculators.
Yep.
I did once buy their like $5 scientific calculator, and it was really bad because sometimes when you push the buttons, they would like fail and they wouldn't work right. So although other calculators might substitute, I wouldn't recommend the, I remember the Job Lot one being really buggy, or maybe it was just the one that I got.
That's why at work I always say, welcome to Job Lot.
Which one do you work at, Caitlin?
I work at the Wakefield one. I left my EMT job for now just to do something low key like that. So
yep.
I just wanted to spare you the time, whoever needed the Casio, that it's not going to be there.
So I noticed Vincent got the right answer. Can you hold that up, David? I want to see if you're getting it. Yeah, cool. And Mikey, how you doing? Did you follow? Did you know how to do that? Or you were lost? All right. Well, then we got to do this together, okay? So let's see here. And this is for the people watching later on who also forgot. We're going to start by plugging in the A, 39.5. And then we are going to cube it. Now, I'm having some focus. Remember how I had to adjust, like fix my focus? The X cube, you have to hit shift, but it's above the backspace key here. So Mikey, we're going to hit shift first, and then we hit backspace to X cube. You got that? Now we're going to square root. You'll notice the square root is in orange. So once again, you have to shift square root. Hold it up. Show me that you did it. Yeah, cool. All right. This stuff is not hard. You just got to figure out where your square and your square root key is. I guess, so the answer was what, 248 years or something? And notice that if you put in the AUs, years come out. Let's try it the other way around too, just to make sure that everyone's got it in the reverse direction. I need to erase this. Okay. Fair enough, Mikey. Those are the jitters we're trying to work out. Yeah, you forget to cube, forget to square. All right, I'm erasing this. We'll just try one more. If instead you're given the period, right? So I believe Mars has a period of 1.88 years. If we want to find A, the average distance, we would write A cubed is equal to P squared. They have to be symmetrical forward and backwards. And then we take the cube root of both sides. A is the cube root of P squared. And then I plug in the cube root of 1.88 years squared. The order of operations doesn't matter because according to PEMDAS, these are both powers and have the same order of rank, but I like to do the inside first and the outside afterwards. So just to save some time here with Mikey, 1.88. This time we're going to hit the square first, which is that key, no shift, just hit square. And then we're going to do the cube root, which is above the plus minus. We're going to hit shift and then cube root and pow, 1.5 astronomical units comes out. Notice that this is a magical formula where years go in and AUs come out and vice versa, okay? So that was just a little introduction because some of you might not have used a square or a cube before. Don't get freaked out. It's not a big deal. It's just a button, okay? All right, glad we had that talk. Now you know Kepler's laws of planetary motion or something. And we're going to proceed to build off that and learn more about the orbits of planets. However, to do so is going to require a leap forward of another 100 years in time, where we eventually get to the works of Sir Isaac Newton and his discovery of forces, proper laws of motion, and gravity. So let's have a quick discussion of that for a second. Can I erase this? Is everyone okay? All right. I'm trying not to go too slow or too fast here. Let me just check my clock so I don't burn this day away. Okay. So we're going to transition now. The Keplers Laws was a little section from chapter 3. And we don't have to read all of chapter 3 because we're not doing the full history of astronomy. We just need Kepler's Laws. And now we're going to focus on what the book would have as chapter 4. And it's sort of like Newtonian mechanics. Newtonian mechanics means we're going to spend an entire chapter on the works of Sir Isaac Newton, the famous Enlightenment philosopher, mathematician, physicist, maybe the most famous physicist of all time. Him and Einstein are kind of tied for who is the greatest physicist of all time. And Sir Isaac Newton, he gave us a number of profound concepts that we need to have in our toolkit to understand how stars work. On a sort of general broad sense, Isaac Newton sort of codified the conception of a force, and the units of force are named after him in his honor. But for the purposes of our lectures today and on Thursday, we're going to break down his works into two broad categories or two broad discoveries. The first are his 3 laws of motion. And the 3 laws of motion were, like Kepler's laws, a set of rules that give us good judgment about how bodies move when they are pushed or pulled, okay? By the way, in a loosey-goosey sense, a force is a push or a pull. Go ahead and write that down for now. So his 3 laws of motion describe how bodies move when they are subjected to an arbitrary force. In other words, once you learn the 3 rules, if you carefully apply them, you can work out very complex problems. So if you take a cannon or a rocket launcher and you apply a force to some projectile, once the force is specified, Newton's laws of motion will tell you how the body will move through space, what distance it will travel before it comes to rest, and other such things. It just prescribes how a body will move when you give it a push or a pull. And the reason why this was so important is people had a lot of goofy ideas about the motions of bodies before Isaac Newton cleaned it all up, all right? We need to have a discussion of this because the definition of a force is encoded in the 3 laws of motion. He also gave us a separate but relatable concept, and that is his universal law of gravitation. I think what might be confusing is that both his 3 laws of motion and his laws of gravitation were both laid out in the same famous book, a book known as the Principia Mathematica, or sometimes just the Principia. I found a copy of it laying in a hallway in CCRI a couple of years ago. This is a work of physics that is so important, it has transcended even physics or science and now become considered almost like a work of philosophy. That's how deep this thing goes, okay? And my point is, it contains his laws of motion, but also a separate thing, the law of gravitation. And the law of gravitation will be your first exposure to something called a fundamental force. A fundamental force is not arbitrary. A fundamental force is not created by humans. It's a part of the machinery of nature itself. In other words, fundamental forces are mysteries of nature. Nature herself invented gravity, and it is our job to understand how nature does this. We are exploring her secrets. There are a number of fundamental forces which other things can be broken apart or broken down into. Do you guys know how many fundamental forces there are? Have you ever heard of the fundamental forces? Or it's kind of like a thing.
Isn't like electromagnetism one of them?
That's one of them. When I was a student, they were called the 4 forces of nature. Although, in the time since I was a student to now being, I suppose, a mature adult, the 4 forces of nature have collapsed a bit, and we have started to see that there are relationships between them, and they're not as separate as we once thought. But just for historical purposes, sorry that I'm an old fuddy-duddy, but the 4 forces of nature were gravity, yes, electromagnetism describes how magnets and electricity work. The other 2 are related to the nuclei of atoms, and it's the strong nuclear force and the weak nuclear force. Believe it or not, in our quest to understand astronomy, stars, and galaxies, we will eventually have a somewhat intense discussion of all 4 of these forces. Gravity is the original fundamental force that was discovered, and it still remains mysterious, the most mysterious of the 4 forces today, because we have since discovered, using particle smashers like the Large Hadron Collider, we have since found relationships between these 3 forces. These 3 have been combined, well, actually 2 and 4 were originally combined into the electroweak theory. And today, these 3 are related by something called the standard model of physics. This is the new hotness in physics. The standard model of physics is a framework of understanding how electricity, magnetism, nuclear forces all kind of work together to govern the behaviors of particles. We have yet to this day to find a way to combine gravity into these other three forces, but it's one of the most important and active areas of research on the front lines of physics. It's cool because astronomers get involved in this too. Stop there for now. Let's get into, do I have time for laws of motion? Oh yeah, I get a little bit of time. Before we do our laws of motion, we have to do a little bit of background work. And I might have time to lay that groundwork so I can get into the nitty gritty on Thursday. And the homework on Thursday is actually going to be a bit of a step up for us. It's going to be kind of wild. So let's do a little background that I think will help us. May I erase, students? Okay. Okay, the sooner I get to the math stuff, the better. But we'll make our job a little bit easier by just doing some background stuff. In chapter 4, we're going to be using some new units for the equations or for the formulas in chapter 4. And it's something called the MKS system of units. You guys can think of it as sort of standard metric units. Although there are many systems of units within the metric system. When we deal with physics concepts, at least in terms of mechanics, 3 of the fundamental quantities that we consider are length or distance, mass, and time. And many complex quantities like forces or energy, they can be broken down into combinations of length, mass, and time. And the standard units that we're going to use for length will be the meter. The standard unit of mass will be the kilogram. And the standard unit of time will be the second. These are the units that we want to convert things into before we plug into our formulas. Because they begin with the letters M, K, and S, we call it the MKS system. Here are some conversion factors that I know will come in handy. For length, 1 kilometer equals 1,000 meters. That will come in handy. Probably the 3 that we'll use the most often are that, the astronomical unit. Now, we know that it's 150 million kilometers. If we convert that to meters, it's 150 billion meters. And, well, I've kind of posed myself here, but let's put it up here. The other one is a light year, 9.5 times 10 to the 15 meters. These are slightly different than the conversion factors that I gave you before. Before I gave you an AU in terms of kilometers, before I gave you a light year in terms of kilometers, but I figured since we're talking meters, maybe those will be helpful for you in the future. Most things we start off with in kilograms, so that shouldn't be too much of an issue. A kilogram is, you know, similar to the heft of a brick. I have a test kilogram that I like to hand around class, but I don't have it with me today. Maybe I'll have that on Thursday. For units of time, I want to tell you guys a really handy conversion factor. I'm trying to give you some useful stuff. Although I like to have students figure it out for themselves, in the interest of time, let me tell you the number of seconds in 1 year. Turns out to be a really helpful conversion factor. 3.15 times 10 to the 7 seconds is a year. Astronomers like to remember it with a little nickname. they think of a year as being approximately pi times 10 to the 7 seconds. That's kind of the joke. These will all be helpful to you throughout our lectures, and I thought that might be a nice thing to do. Okay, now that I've mentioned our standard units, let's go on and let's talk about some basic physics concepts that we need before Newton's laws of motion, and let's pay special attention to how they fit into the MKS system. Wow, guys, I'm losing my damn voice today. Okay, I would like to just get these last two little things done to set us up really well for next time. Can I erase here? All right. To discuss Newton's laws of motion, we are going to have to discuss motion. And that means we're going to have to talk about speeds, velocities, and accelerations. If you've ever taken a basic physics course, this would have been the very first place you start. Just out of a curiosity, I wanted to take physics in high school. How many of you took a high school physics course? I'm just curious. No?
Me, and I barely made it.
Yep. It can be very, David's like, oh, hell no. Usually in a room full of my students, half of them or so will have made it through one. And I happen to have a really cool high school physics teacher who made it super fun and super awesome. And I'm so grateful for that experience, because if the wrong person, I like your sweater. That's a cool Star Wars jumper there. If the wrong person is doing it, it can be such a horrible experience.
It was for me, because my teacher, he was like super old school, and this guy did not want nothing with like opinions outside of like, nobody could ask like really like questions. I like to ask questions, but this guy was just upset all the time. And I was like, you don't want to be here, so neither do I.
Well, I mean, that's a real tragedy, and that person was probably doing it wrong. On the other hand, you will yourself one day discover, if you become a teacher of young hormonal 16 to 18-year-olds, that they're not the easiest group to work with. And naturally, when you're going through those explosions of freedom, creativity, and awakening, the last thing you want to do is sit down and think about blocks and levers and stuff, right? And unfortunately, teachers are also underpaid, and there's too many students, and those things unfortunately can grind people down. That's still not an excuse, okay? You still owe it to yourself.
Nah, it's so good. I mean, for what he taught me, actually made me go to like accident reconstruction school for like the police academy and stuff, and it helped me out a ton.
Okay.
So I like that.
Well, this won't be this. We don't have time to do a full physics course, although we have to do little baby physics. And I'm hoping this will be a more enjoyable experience, but you keep them questions coming, Lionel, and I'll keep answering them. All right. Let's see if anyone remembers anything. Yeah, it's true, David. You know when math is really fun? When you get paid shitloads of money to use it in a job. That's when suddenly you're like, oh, I kind of like this stuff. All right. So okay, so and jobs with math, they always pay better. Okay, so let's review just a couple of quick concepts. We don't have to go too nutty about it, but let's talk about speed versus velocity. This could potentially come up in our subsequent lectures. Anyone want to remind the class what they learned, or have we forgotten the distinction here? They have the same units. The units are meters per second, okay? But they are not the same thing.
Well, speed is like the time rate of where the object's moving along its path, and like the velocity is the direction of in which like the objects move. It's kind of hard for me to like remember this stuff.
Yeah, but you're groping around it, although you're not. You've got the right idea that velocities involve direction. But the way I would think about it, let's see if I have crappy little slides on this, although they're not totally necessary. A speed is a one-dimensional description of motion in that there's a rate, there is how fast, but there is no information about twists and turns or direction, right? Like if I tell a student, it takes me 20 minutes to get to school, or 15 if I drive at 95 miles an hour. Not that I would ever do such a, vulgar thing, but if I did, hypothetically speaking, we imagine me going from downtown to CCRI kind of in a straight line, which of course cannot be true because I've got to take a left and a right and get on an exit ramp. It's never really a straight line. But if you want to just pretend for a second, speed tells you how fast, but really nothing else. So it is one-dimensional. And sometimes that's a good enough description of affairs, right? You're going from point A to point B in a straight line. And probably the equation distance equals rate times time should really be labeled distance equals speed times time. That classic old-fashioned formula means you're not really thinking too much about directions, but you're just sort of you're asking how fast, okay? So speed versus velocity. Velocity is speed plus direction.
Oh.
And if you think about it, Lionel, speed plus direction means you're basically including a two-dimensional or a 3D description of motion, because now you can talk about how fast and in what direction inherently means you've got some kind of a coordinate system, right? With an X and a Y. And you're now going from point A to point B, but the direction matters. There are components in the vertical and in the horizontal direction. That's kind of a crappy description there. Let's look at a better picture. Sorry, that's a crappy little drawing there. Here's a velocity. If you have a sailboat, if it travels 100 knots per hour, then 100 knots per hour are the speed. And in a direction 45 degrees east of north, that's what makes it a velocity, is that you included the directional information. Now, if you think about it, there is a very important situation in which this could matter in astronomy. Consider perfectly circular orbits, which, okay, Earth and the Moon are close to perfect circles, but not quite. But we have many satellites in a geosynchronous orbit that have pretty damn close to circular orbits. In a circular orbit, you actually have, just like Plato imagined, uniform motion, uniform speed, but your velocity is not constant because the direction in which your little spacecraft is pointing keeps changing. One moment in orbit, you're pointing in that direction. Another moment in orbit, you're pointing in that direction. In perfectly circular motion, which kind of comes up, or the concept comes up a lot in astronomy, you have an object with a constant speed, but a perpetually changing velocity. It was the wisdom and the good judgment of Sir Isaac Newton to realize that if the velocity changes, meaning even if the speed is constant, if the direction in which your spacecraft keeps pushing is changing, then that must imply there is a secret acceleration at work. And weirdly, the acceleration is directed towards the center. That is not an easy conclusion to reach if you're the first person to do it. He realizes that something is changing the direction of this arrow and that the direction matters. Okay, so speed and direction versus just speed. That's the difference between velocity. Honestly, you're going to see me use them interchangeably. And oftentimes I write the equation as distance equals velocity times time. And we say, who gives a shit? But we have to give a shit because accelerations can be a part of changing speed or changing direction. And that's an important issue. I'm going to erase here and I'm going to move on to a quick definition of acceleration. This is all some just a little background stuff we have to do, whether you like it or not. Here I go. Any objectors? Let me squeeze in one more little module, which I have 2 minutes for, okay? Let's do a little tidbit on acceleration. We also use A for acceleration and Semimajor Axis, not very helpful. Okay, acceleration is basically a change in velocity. Now, if you say it real correctly, it's a change in velocity with respect to time. But honestly, since everything takes time, if you just say change in velocity, that's kind of a close approximation, okay? However, we can write this mathematically. We can write this mathematically if we consider an object in motion having speed 1 at time 1 and speed 2 at time 2. So we're imagining at time 1, it's at one rate, and then time 2, it's at another. And I've implied that it could be direction or magnitude here. We can say delta V over delta T. This is the real definition of acceleration, where I've used those mathematical operators. The little delta symbol means change, okay? We use delta for change, and what it means, if you remember your high school maths, it means V2 minus V1 over T2 minus T1. And I'll show you a slide in a second. Perhaps the most famous example is something called the local acceleration of Earth's gravity, which is such an important acceleration in physics that we honor it with its own letter, lowercase g. And the local acceleration of Earth's gravity was first discovered by the great Italian physicist Galileo Galilei.
Wait, before you go any further, is that like the gravitational pull of the Earth?
When you say okay, Lionel, in physics, words matter. The fact that you said gravitational pull, a pull is a force.
A force.
This
is velocity, and
this is the acceleration, okay?
Yeah.
And I'm going to show you some slides in a second. I hope I spelled his last name right. Galileo Galilei. Okay. He discovered the local acceleration by famously designing something called an inclined plane. And he rolled a bunch of spheres of different densities made of wood and metal and other things down the inclined plane to study how objects fell in a gravitational field. Okay, I wanted to get some notes into your book. We'll put 2 more in. We're almost done here. Let's take a step back and let's pretend that we were doing a more modern version of what Galileo was up to. Let's imagine that we were trying to measure the change in velocity of a falling object, but let's say we weren't using Galileo's inclined plane, but we were using a more modern device. Like in physics labs, they sometimes have a thing called a laser gate, and they're basically a bunch of little laser tripwires. And when you roll a cart along a track or something, every time you cross the laser beam, you can record position and velocity and things like that. So let me get, where was that thing that the cat was playing with the other day? Because I don't have all my usual, oh, here's something. Okay. Let's say that I went up to the top of my building downtown, and I took this little racquetball here, and I held it right over the edge of the roof. Okay. When I'm holding this thing in my hand, we can all tell that for the most part, the velocity is 0. And that's because if I hold my hand steady enough, it's not in motion. It's maintaining the same position with time. So we know that it's not moving or close to not moving. Its velocity is 0. And if I simply release my fingers, I don't do anything violent. I just try to gently take away my thumb and my finger. The magic of gravity begins. And somehow this particle, by its own volition or by the volition of gravity, however you want to say it, by magic, truly by magic, gravity starts to work and it begins to speed up, right? And so in a weird way, we already know that there's an acceleration because a velocity of 0 is a valid velocity, right? And clearly I've gone from 0 to totally not 0. We already know that there's an acceleration at work. Now, suppose we aren't satisfied there, but we want to take some measurements. If you used a little laser gate and measured the speed as it traveled to the bottom, what you would discover is that after 1 second, it would be moving at a velocity of 10 meters per second. And after 2 seconds, 20 meters per second. And if the building was tall enough, after 5 seconds, it would be up to 50 meters per second, meaning it keeps changing by 10 meters per second every second. Just for kicks and giggles, before we end class, let's put those two velocities and times into our equation. And what I'm really doing here, guys, is this is about units. So hang on with me for a sec. May I get rid of this for just a sec? Okay. So if we want to mess around with little g, and it's going to come up in our class, little g could be computed by doing, let's see, we'll use V2 20 meters per second and V1 10 meters per second. So we'll do 20. And here I'm going to make use of some colors, so bear with me. 20 meters per second minus 10 meters per second. That's velocity 1 and velocity 2. And I'll divide them by the 2 times. The second time is 2 seconds. The first time is 1 second. And I want to talk about the math and then the units. Oh, the math is just stupid, though. The math, 20 minus 10 is 10 meters per second. And 2 minus 1 is 1 second. Obvi, 10 over 1 is 10. But do you guys know what the units are?
Meters per second squared.
Yeah. This is a little trick that I want you guys to pay close attention to. I want you to note the position of meters, seconds, and the second. And I want you to notice that what we have going on here is a situation with fractions inside of fractions. This is going to come up in our class all the time, so we kind of have to talk about this. I want you to imagine that because I can always divide anything by 1 secretly, that there's actually 2 little fractions here with 4 different positions. And forgive me if this sounds a little weird. I'm not really sure how better to do it. The meter is in the top of the top fraction, okay? The first second is the bottom of the top fraction. The second, here maybe I can write this a little cleaner. I'm just telling you this because I've learned the hard way that it's helpful. The second is actually in the top of the bottom fraction. And this imaginary number 1 is in the bottom of the bottom fraction. Now we have to be able to compress these into a single set of units all the time. And one of the rules that our friend who correctly guessed meters, or didn't guess, who knew that the units were meters per second squared, is using a very important rule. The bottom of the top fraction should end up in the bottom. the top of the bottom fraction also stays at the bottom, so that the units are actually meters per second, okay? Or the eventual units that we want, the units of acceleration, 10 meters per second squared. It might be helpful for you guys to write down a little doodad with me here. I don't want to sort of draw this out because I want to end lecture here, but could you just reproduce the following little rule that I think will guide us going forward? Whenever you're confronted with fractions inside of fractions, so let me use friendly colors here. A divided by B divided by C over D. The resulting fraction, simplified, will look like this. Both A and D will end up on the top. C and B will end up on the bottom. There's a good chance many of you knew this, or you might have learned it at some point, but I've discovered it's a great thing, and students have really said this has helped them to just remind ourselves about this rule. The top of the top fraction is the top, bottom of the top is the bottom, top of the bottom stays in the bottom, and most tricksily, the bottom of the bottom fraction flips back up to the top. There's a little sign on one of the professor's doors in the math department. It says, 3 out of 2 people are bad at fractions. And not only is that funny, but really true. Okay, so it's good to have some quick rules like this that will help us going forward. Meanwhile, to conclude our class with some background stuff, don't forget that the units of acceleration are meters per second squared, and that the local acceleration of Earth's gravity is 10 meters per second squared. And one of the big discoveries that Galileo made is that all objects accelerate to Earth with this value, no matter what the object is, whether it's a dump truck or a pencil or a rocket ship or anything, all objects fall to Earth with this acceleration. Like this. Maybe we can say more about that next time. Okay, basic stuff you got to know about. Next time, remind me, next time we want to get right into Newton's laws, all of them. And there's going to be some insane new formulas. I expect Thursday to be a big day. All right, we've busted our lecture budget for the day, and it's 1:12. Sorry about that. I didn't realize how long I was going over. What do you say 1:20 we'll get going? Our lab today is quite simple, so I think we can get done pretty close to 2. We like it? Okay. I'll take a little pause, and I will see you guys then. See if you can find some cardboard, some string, and some thumbtacks. That would make this a lot better. If not, then print out my ellipse that I made for you, okay? All right, be right back. Okay, everyone, welcome back. We're about to do lab 3, where we're going to make a model of an ellipse using the thumbtack and string method, which is kind of classic. Once again, to do this lab, ideally you'd have a piece of cardboard that you can put your printout of page 5-5 of that lab packet. It should have 2 focus points. It should have places to put these quantities. You'll remember that at some point we talked about making scale models, and the idea is that we're going to be making a scale model of a planetary orbit in which 1 centimeter is equal to 1 AU. And I'm going to walk you through that. If you are doing this correctly, if you actually manage to get a little loop of string and tie it, your numbers are most likely going to be a bit different than mine. I'm pretty sure that the ellipse that I gave you, if you are not capable of drawing your own ellipse for one reason or another, I did provide you with one, which I think is a little bit of a cheat or a cop-out, but I suppose I'll accept it. This PDF has the 5-5, the page that we'll need. And this ellipse drawing was just in case a person could not find string, or I have seen people who had difficulty making the ellipse for one reason or another. I'll walk you through the doing of this, however. Let's go ahead and let's activate my iPhone here. So we're going to share screen, and I should be able to connect here using my screen mirroring. Okay. So if you can see my camera, okay, let's add a tiny bit of light here. Get my holder out. As always, our first step should be to print our name. Hold on a second here. I don't like writing on the cardboard. Let's print our name. And let's write AS1020. Don't forget to put your section, either 001, 102 is the night class, or 600 is the distance learning online class, all of which are following the same program. Oh, geez. Tape holder. Don't forget.
You said 102 was the night class?
Correct, Dennis, 102. Don't forget to also write lab number 3. This turns out to be real useful, and we have to go back and check if we forgot to submit something or whatever, okay? Okay, so we'll get right to it. In our scale model of the solar system, 1 centimeter will be equivalent to 1 astronomical unit in space. So we can either take our measurements in centimeters or in astronomical units. Our tolerance, our measurement tolerance, our tolerance will be plus or minus to the nearest 1/10 of a centimeter, or 1 millimeter. Sorry, nearest 1/10 of a centimeter. In other words, all measurements, when taken with a ruler like so, should be made to the nearest little millimeter tick mark, okay? Now, to start, oh boy, where'd that, oh shucks. Where did the loop of string go? Just a moment while I have a major freak out here. I just had that thing. What? Oh, here it is. Okay. Whew. So here's a loop of string which I've tied with a knot. And the original length of string was probably close to 30-something centimeters. Now, when stretched edge to edge, mine is somewhere between 14 and 15 centimeters. So it can be anywhere. It can't be too big or you'll go off the page. It can't be too small or you won't cover the focus points. But mine actually tops out around 14.6 or 14.7 centimeters. So if you made it 30 and then you tied it carefully, you might get something like that. Just out of curiosity, how many of you actually have some string and cardboard? And oh, David, cool. Anyone else? Hey, Mikey, all right. All right, oh, and Caitlin, I'm impressed with y'all. Okay, now we're gonna grab a couple of thumbtacks. I will choose green for science or nature. And I'm gonna place the 2 thumbtacks at the 2 focus points. And I'm gonna kind of really drive them in so that they're sort of deep into the cardboard here. Try to keep them real perpendicular, drive them in deep. Okay. I'm going to put the loop of string underneath the thumbtacks against the metal. I'm going to hold my pencil taut, and I am going to drag around the page. And if you do it carefully, it should perfectly reconnect, and we should have made a lovely little model of an ellipse. And this mathematically satisfies the criteria for an ellipse, because the perimeter of the triangle made by F1, F2, and any point on the ellipse is constant. All right. How'd you guys do? Those of you who were doing this, did it come out okay? Normally I kind of patrol around. Caitlin, what happened? Can't hear you.
My cardboard sucks, so I'm trying my best.
Do what you can. Hey, Dennis, what you got?
So I don't have a thumbtack, so I'm just like literally using sewing needles. But how do you make the circle again? You just put the string around it, and then you just do a little.
I mean, yeah, the trick is you've got to have something with enough grip so that when you put the string against the metal, I'm not sure if you'd be able to catch it against sewing needles. You want the pencil to be able to catch, and you want the string to stay tight as you drag around the page, right?
Oh yeah, no, these will be fine. They're not like super. They're pretty good needles. So
Okay. If you guys pull it off, I'll be impressed. Caitlin, what was your situation?
My cardboard sucks.
Oh gosh,
So-
why is it so lumpy?
It's because it's from an Amazon box.
Yeah, you
So-
kind of have to have some. I've got a pretty, like a pretty thick piece of cardboard, I guess. Like
I
I
mean,
think,
at least it made an oval, so I can't be too mad.
well, I could.
True.
Do you want me to get me? I mean, hold it up. Let's see what we're dealing with here. I'll tell
I'm trying
you.
to fix it. It's
I'll
the
tell you
top
this.
part.
If this was in lab, if we were in lab together, I would not settle for that. I would make us do it right. But I'm also trying to take into account the fact that even though these are simple materials, you may not have them handy. Yeah. David.
How far apart did the thumbtacks have to be?
On this page, they were 12 centimeters to within a millimeter. And so that was pretty good. Although I could settle for less if you had a smaller piece of string.
I do.
I'm just trying to think of what Caitlin might be able to do. So are you saying, Caitlin, that your cardboard was so thin?
Yeah, my cardboard's more like lumpy than it is like
Could you
straight.
stack, could you stack it on top of like a pad or a book? The kind of cardboard that you'd have in a big box, like a printer paper box or something, would be ideal.
Hold on, I got a notebook. That would
Yeah,
work.
see if that helps. How about the other folks? Mikey, Vincent, let's just talk about it here, because I don't want to be blasting ahead if you guys are struggling. Maybe I'll put this on pause until you guys have your situation together, shall we say. Where's the recording? Resume recording. We should now be recording. Okay, everyone had a couple of minutes to fiddle around with their cardboard and their paper and stuff. Hopefully now you've got some type of an ellipse. I am going to remove the thumbtacks, and I'm going to remove the string, save that for later. And I'm going to take the cardboard away so that I can work directly on the table for the next parts. And I should be able, in theory, to turn this sideways, but I've noticed that it doesn't. It used to be that if I turn to this camera sideways, it would go sideways in the Zoom recording. What if I go upside down? But it's sort of not doing that anymore. My iPhone knows it's rotating, but Zoom doesn't know that I'm rotating. I wonder if you have to do that manually now.
Can you tell me how this looks real quick? Because I'm really going through with this stuff.
Yeah, hold on. Sorry, I thought, here, show me again. Hold it up. Well, Lionel, to be honest, looks like shit, but you know, first of all, do you know where your thumbtacks are?
Yeah, I got them. They just fell out of the cardboard right
No,
now.
but like, in other words, I can identify where my focus points are, so hopefully you can too. Show it to me again. I'm trying to see if I can put up with that. What happened with your string? It didn't say, I guess it's not the worst. No, I mean, honestly, no.
I'll remake it again because I could
Nope,
just
nope,
watch the.
nope. Lionel, fine. Let's go with it. Okay. I'm cool with it. I changed my mind. It actually doesn't look as bad as I thought at first. I was kind of teasing you. Do you know where your focus points are? Because that's going to be very important.
Yeah, I know.
Okay.
I know where they are.
Everyone follow along. In Euclidean geometry, 2 points make a line. So we're going to use these 2 points to make a line that goes from edge to edge of the ellipse, but no farther. So I'm going to start here. Sorry, see my phone here. And I will go all the way to the edge of the ellipse, but then I stop. This is your major axis. And our first job is to measure the length of the major axis. So I'm going to do that with mine here using a ruler. So first, I make sure that 0 is right at the edge of my line. And then I clamp it down very carefully. And just to make sure that you understand, what would you guys say the measurement is there?
18.9 centimeters.
I'd say 17.8. If you look, there is no line at 17.9. The tick mark before 18 is blank. Cool? All right. So I'm going with 17.8. That's my personal estimate. Now, I'm going to put it in AU because it's a scale model of a planetary orbit. We need to mark the midpoint, right? So 17.8 divided by 2 is 8.9. So I'm going to go to 8.9, and I'm going to mark that midpoint as best I can. That's my center, C. I'm going to now draw my minor axis in perpendicular to the major axis, and some care must be taken to make sure that you are perpendicular. I like to use these little inch lines to kind of guesstimate to make sure that my line is perpendicular. I kind of make sure that that's parallel there. Now I've drawn in my minor axis. I could have been a little more perpendicular, to be honest, but that's close. Let's do some labeling. Major axis. Let's do some labeling. Minor axis. Let's choose one of our focus points to be the sun. I think I'm going to choose F2. Ooh, I'm even going to use a little circle maker for this because I'm cute like that. Cute like that, yeah. And I will label that as the sun. Even put some beams of fire coming off it here. Not fire, but sunlight. Okay. It's my sun. Okay. Let's for kicks and giggles, let's put a planet on there somewhere. Just for kicks and giggles, you know. Planet. Okay. There's my. There's my planet. Now, planets tend to orbit the sun counterclockwise. Keep your pencil real sharp. So I'll draw the direction, assuming we're looking from north pole of space. Planet is orbiting counterclockwise, okay? Let's see, we've got to measure our perihelion. Do you guys know where the perihelion point is on the ellipse? Where's the perihelion point?
The closest point to the sun
On the ellipse.
on the ellipse.
So let's mark that. As our perihelion. And likewise, the farthest point from the sun on the ellipse is our aphelion. Now, although I gave you formulas for calculating perihelion and aphelion, we don't know what our eccentricity is yet. So we're going to directly measure perihelion and aphelion. Do you guys know how to measure perihelion? What do I measure from and to? What do I measure from?
It's from the focus point to perihelion.
Yeah, to the perihelion point. So let's see, making sure to use the centimeter side. Don't screw that up. Fudge. Okay. It's either 2.9 or 3.0. If I go right from the center, it's actually sort of in between, but I only need to a tolerance of 1/10 of a centimeter. I'm going to assume I can choose 2.9 or 3.0. I'm saying it's a wee bit closer to 3.0, so I'm going with it. Okay. Now we're going to measure our aphelion. Now the aphelion, we go from the edge of the ellipse, the aphelion point, but we go to F2 again. We got to measure it to the sun. So all the way over here. What would you guys say? I'd say 14.8, I guess. It's pretty damn close. 14.8, 14.9. We'll do 14.8. Those kind of add up, so that looks nice. Now we're going to measure X. First, let's label X. X is the focus offset, and it goes from center to the center of the sun. Okay. So that's my X. And let's label A. The semi-major axis is half of the major axis. So it like that. Okay. First, I will measure X. For my page, I got 6.1 centimeters, or 6.1 AU. For my A, center to perihelion, I get 9.0. Please ask questions if you're getting confused here. For me, this is pretty straightforward because I'm familiar with ellipses. I hope it is for you guys.
Could I just see like the whole page real quick?
Yeah, I wish I could go sideways, but for some reason, my phone goes sideways, but it used to be that Zoom would flip with me. And either they've changed it or they've disallowed it, and I'm not sure which it is. That's a nice way to frame it, but now it's probably sideways for you guys. I bet you can manually change that box, but I don't want to go on a trip to video settings land. Of course, that's exactly what I'm doing. Share screen. Enable side by side. Oh, I don't know. Okay. Do you guys remember the formula for eccentricity? Do everything over here.
X divided by A.
That's right. So let's do our maths over here. For X, I got, and you guys might want to use your own numbers, 6.1 AU. For A, I got 9.0 AU. And then if I divide those two, 6.1 divided by 9.0. How many sig figs should I keep?
2.
That's right, 2 on top, 2 on bottom. So in my case, I would round to what?
0.68.
Right, nice. Now, are there any units associated with this?
I don't think so.
No. This is a key idea, a key concept, is that eccentricity is a unitless or a dimensionless quantity, because at the end of the day, it's like a percentage. It's percent squishiness. In my case, 68% squishy, which is more than you'd think considering the egg-like shape to it. Although I did say 0.5 was close to an egg.
For my E, I only had one unit on top and one on the bottom, so would I only keep one significant figure?
Wait, you should not have 1 unit because I demanded a tolerance of 1/10 of a centimeter. And that would imply that your ellipse is so small that it did not go past 1 centimeter. If you only have 1 significant figure, then I hate to say this, but you did a shite job measuring. How is that? Who's talking to me now? David?
Yeah.
David, how is that possible? Can you walk me through that?
I don't know. I just measured it from how I drew the.
Well, hold on. So, part of this is employable skills, and measurement is an employable skill. If I tell a person at Home Depot, I want you to cut this 2x4 to a tolerance of 1/16 of an inch, they're supposed to know that the cut has to be that good. I'm telling you that I want a tolerance of 1/10 of a centimeter. So let's just get down to brass tacks. What did you get for your X?
I had 5.
So let me explain why that is complete horseshit for me. You mean 5 centimeters, I hope?
Yes.
Okay, I don't think you understand what 5 centimeters means to me. 5 centimeters to a scientist means my measurement is somewhere between 4 and 6, and I think it's closest to this line, but I'm doing such a slovenly job that I didn't bother to look down to the nearest tick mark. So that bothers me.
Okay.
I want to know, is it 5.0? Or I bet if I was at your house and I measured it, I'd find something different, which troubles me. Can you hold your camera might be stuck to your computer. Could you just do it again? Are you sure you're using centimeters first and foremost? Second of all, are you telling me that it was 5.0? In other words, it was not 4.9 or 5.1? You need to be 100% sure about that. To the nearest tick mark.
Maybe like 4.9, more like it.
Okay, and I'm not asking you to change stuff, but see, like on my first one for my X, it was actually a bit closer to 6.1 than 6.0. So I recorded it as such.
Okay.
But if you look, mine was actually closest to the actual number 9 slot. That doesn't mean I can't have 9, but I'm specifying 9.0 because it was closer to 9.0 than 9.1 or 8.9. In other words, you don't have to, it can be on the line, but then you say 5.0 to distinguish, right? So was it closer to 5.0 or closer to 4.9 in your best judgment?
I think it looks more towards 4.9.
Then that's what you record. That
Okay.
means 1/10 of a centimeter precision. So in your case, I'd expect your A to have the same level of precision or tolerance. Okay, that was a great instance. Believe it or not, David, that was very helpful for my video. So you did me a great favor here. This is an issue that many people have, and I wanted to address it.
Okay.
Okay, now it's time for us to do the period with the old p squared equals a cubed routine. Okay. So on your page somewhere in the margins, p squared is equal to a cubed. Just like we did in lecture today, p is the square root of a cubed. And my a is 9.0 AU. I keep bumping the damn the phone, sorry, my camera stand. So p is the square root of a cubed. And now I'll actually substitute in my values. P is the square root of 9.0 AU cubed. And I'm going to do this all in one clean, crispy shot. 9.0. And first I'm going to cube it. So to do that, I do shift x cubed. And now I'm going to square root it, which is here, shift square root. Now mine turned out to be elegantly, because of the nature of 9 cubed, 27. And do you guys know what the units are going to be?
Years.
Yeah. Now I want you guys to have a similar precision here. You'll notice that 9.0 is 2 sig figs, and so is 27 years. Honestly, this was not a great example. Let's imagine that I had gotten 8.9 instead. I would do 8.9 shift cube, then I would square root it. And if my answer looked nuts like this, I would round to 27 because I could still only keep 2 sig figs. So the 0.5 would round 26 to 27 because I only had 2 sig figs going in. Unfortunately, my example didn't look so great because it came out to be a clean 27, and there is no such thing as clean. It's about precision. So if you get a kooky number like this, you round to 2 sig figs, presuming that you had 2 sig figs going in, which per my discussion with David, you'd kind of freaking better, right, David? All right, he understands me now. And this, my friends, is it. This is all I wanted us to do, to make a nice, neat, very careful model of an ellipse where we can identify perihelion, aphelion, major axis, minor axis. You better have all of this if you want your 10 points. Label X, label A, measure perihelion, aphelion, major axis, measure X, measure A. Calculate your eccentricity using that formula. Calculate your period using p squared equals a cubed. Round units, and that's that.
For P, I got distracted when you were going over it. Just a clarifying question.
Yep.
We're trying to find the A, right?
No, we measured the A
So,
because
okay.
we measured from here to there. That is the semi-major axis.
Okay.
So you should have measured from perihelion to center. Oh, if you want, let's mark the center with the C, one last thing. Not totally necessary, but that's the center point. There was another part to this lab, but it takes a long time, and we've already used up a pretty good chunk of time. So in the interest of letting you guys out of your, this is the most important thing, especially for the test. You better have this memorized, okay? Or at least what's going on, properties of an ellipse. It's not too much to remember. Okay, submit under lab 3. Thank you much. Any other thoughts, comments, or concerns? I'll stop the recording, and if you guys want some detailed help on your ellipses, I'm down to offer that. Any student who's working on this later on tonight, feel free to give me a ring-a-ling, and or we could even Zoom, and I can help you through this if you want that help. I guess unless there's any questions that the other students would benefit from, I'll stop the recording now.
Yeah,
So I just have
I'm just gonna do it again because I don't feel comfortable with like this paper, and I don't feel comfortable with what I'm about to hand in. And trust me, when I have a bad feeling about it, it's not good.
Well, this actually might benefit the other students. Lionel, can you show me what you have? And then I can say, it might be helpful for students at night watching this to know if I'll put up with it. I am trying to make allowances for the fact that you guys are doing this at home without the exact tools that I have and without a pair of hands. So, you know, because sometimes in lab, I can kind of walk around, you'll discover this, and I can help hands-on.
It's great. Wait, give me a second. Let me just get rid of some stuff. It looks messy and it looks shitty.
Well,
I just don't want.
maybe I'm okay with it, okay?
Not good.
Honestly,
I want to do it.
Wait, can I see this? Hold it up higher because you're not. Okay, here's my beefs here. Actually, I would accept this, Lionel, but can you hold it back up again so that other students, bye, Mikey. Slide over because you're not framed well. No, the other direction. Yep. Okay, you do not have your A labeled. That's an issue for me.
Okay.
You need to, but I could, if you want to do it for your own sake, to feel good about yourself, Lionel, then I'm cool with that. But I would actually accept that, considering that you're doing it at home in your bedroom without me around. I think that it's a passable job. Don't listen. I was kind of picking on you earlier just for comedic effect.
No, that's okay. The thing is, my gut feeling, yo, that's not what you could do. You could do much better than this shit.
I mean, I do kind of agree with you. If you have time, redo it. But if not, I'm okay with it.
I got time.
You have to label your A. Make sure you have all those things that I have labeled. And once again, I can.
Yeah, I'm definitely gonna do that because it's kind of like messy. I don't like how it looks. If I don't like how it looks, it's not. Cool.
Yeah, you want to be proud. And that's right. Taking pride in your workmanship is one way to get into school and to do it right. That's the right spirit, is to be like, hey, I want this to be as good as I can be for myself to prove that I can do it right. Now, if yours looks like mine, then that's definitely good. You'll notice that my ellipse actually it's a pretty good ellipse. On the other hand, I've had years to kind of perfect this technique, so don't feel too bad if yours isn't quite as good as mine. But
no, it's okay. I'm just gonna go print out that same paper at the library. The library is literally down my street. I can't hand this thing for me. Look.
Really, the secret might be getting the right thickness of cardboard, and the side of a paper box would be good. And then getting the right string. You'll notice that this string is thin. It's got the consistency of maybe
this piece of garbage.
Yeah. And the knot has to be tied good. I think the lab tech tied this knot. I'm not the best knot tire, but I could probably make it work.
Okay.
So I don't know. This is just a standard piece of twine or something. Do what you can. I will forgive as long as the major measurements are there and stuff. Okay, I'm going to stop the recording, but I'll stay on for just 2 more seconds. See you guys on Thursday.